Alright, we'll see what happens here. I'm using a backup phone to make this. Unit 3 worksheet 1 static force key. I'm just going to quick fire this up, get this made. Some students were asking for it. I will give some advice. 85 kilogram canoe. Alright, so I'm pretty much just going to get right at it. Toggle right, pull to the right by a second chain. So it ends up looking like this. I'll put it on a coordinate system. Alright. Okay. 55-degree angle at the ceiling, which means this is 55. So I've already gone over this one, which means this is 55. And a video, I think. So we'll just do this. Negative 850. Alright. Oh, I guess I should have maybe put that more centered, but that's okay. Alright. So let's call this FT1 and FT2. Chain, tension, all kind of the same thing. First thing we do here, FT1X, find the X and Y components. It's going to be FT, so X component here, 55 is going to be cos of 55 degrees. Now you might say find the X components, you don't know the tension, so how can you do that? Well, you're right, but the whole point here is I'm finding it in terms of FT1. So the X component is down here, right? FT1X, and the Y component's up here. Alright, if I had a different color pen, that would be nice. FT1Y. They're dashed arrows because they aren't extra forces, right? They're not extra forces, they're just the components or shadows. Alright, how much weight must this chain be able to support? This is crazy. I might have paused this and closed my door. Alright, here we go. Spanish class across the hall gets a little wild, so I had to pause this. Back at it. Close the door. Alright. How much weight must this chain be able to support? Basically, you got to see what the tension is going to be in either rope 1 or rope 2. Alright? And then go from there. Alright, so let's do X direction, Y direction. Alright? We already did this, but anyway. X direction FT2 plus FT1X must equal 0. The Y direction FT1Y plus FG must equal 0. So FT2 we don't know. FT1X we know only as FT1 times the cos of 55. Now, you might say, how does that help you? Well, you'll see in a second here. FT1Y we know is FT1 times the sine of 55 degrees minus 850 newtons equals 0. Now, when I put the numbers in here, then I make them negative. Alright? Components in here, I would make this negative if it was a negative component. In fact, over here, I should have made this negative. Alright, so I'll go add a bold negative sign. I gotta get some white out, but oh well. So that should be negative, and that should equal 0. Alright, so now I take this one, solve it for FT1. FT1 equals 850 newtons divided by the sine of 55 degrees. 850, oh boy, 850 divided by the sine of 55. Make sure you're in degree mode. Alright, equals 10,040 newtons, 1,040 newtons. All right, when I take that and plug it in over here, so FT2 equals FT1 times the cos of 55 degrees. All right, so bring this over here. And, you know, you can jump right to this line, right? You can say the total forces acting to the left, the magnitude of the total forces acting to the left equal the magnitude of the total forces acting to the right, and so on, or switch the way I said that. You can do that. I prefer to write sum of the forces equals 0. That's really up to you, but if you're kind of lost, like I know a lot of you are, try my way. All right, so FT2 must equal 1,040 newtons times the cos of 55. I'm just gonna, about 600 newtons, yeah, I remember that. So this chain must be able to support at least 1,040 newtons. All right, coin resting on the physics book. All right, so coin on the physics book. I'm going to make a drawing of this one before I might say, why didn't you include a drawing? I don't remember. Maybe I should make drawings of these here for you. That would probably help. Probably would help. 13 degrees. Now I made a video about inclined planes, so I'm not going to spend too much time talking about why we rotate the coordinate system. Anyhow, force diagram, FG, Fn, and force of friction. We put our coordinate system parallel to the plane, parallel and perpendicular to the plane, our x and y axis. All right. Where does the 13 degrees come into play? Well, that's this angle. All right. If the coordinate system had been started off originally vertical, that y-axis, to make my x-axis parallel to the ramp, I have to rotate it 13 degrees. So I made this way too not to scale. Rotate it 13 degrees. That means the y-axis would also have to rotate 13 degrees, which makes this angle 13 degrees. And what that does is that gives FG an x and y component. So I always like to do that just kind of right to the side of the force diagram. Any angled vectors break into x and y components. All right, so here's your x and y components there and there. FGX and FGY. X and y don't necessarily mean horizontal and vertical with respect to the ground, right? They're all relative. So anyhow, FG x is going to be FG times the sine of 13 degrees. All right, FGY, I guess I could put in mg for FG, but I guess I'll do that, guess I'll do that on the next part. All right. So now, same thing we did up here. X direction, Y direction. About 5 minutes, not even 4 minutes. So I'm going to try to pick up the pace here. X direction, we have FGX plus the force of friction must equal 0. Y direction, we have Fn plus FGY must equal 0. FGX, so I'm going to make that's down the ramp, I'm going to make the positive direction. So FGX is, I'm going to put in mg sine of 13. Force of friction is mu times the normal force plus mu Fn. I don't know what the normal force is yet, so I'm going to leave it like that. Oops, I have to make that negative. My bad. Minus mu Fn, because the force of friction is going up the ramp, the negative direction. So when you start putting in the formulas, you got to put the right signs on them. So over here, Fn, FGY now is going to be plus negative mg cos of 13 degrees. You know. Now, why did I do it that way? Plus and negative mg. Well, I could have done that here too. Plus negative mu Fn. It just ends up being Fn equals mg cos of 13 degrees. And I probably should have just left it theta to you know, make it a general equation in the end. But we're looking for a specific number, so I guess I'll leave it. I don't know m, right? So that's why I haven't put any numbers in there. So now we got this, we're going to put it in over here. So mg sine of 13 minus mu times mg cos of 13 equals 0. Alright. Mg sine, and I basically did this one in the video, but mu mg cos of 13, mg's cancel, mu equals sine 13 divided by cos 13. I guess I better put degrees on these things, which equals tangent of 13 degrees, which equals 0.23. It's our coefficient, 0.23. Cool, interesting one. And then the final one, try to finish up here. Bell's gonna ring in 15 seconds, and I'll have engineering 2 kids coming in here. But I'll get this done anyway. Block B weighs 711 newtons. Coefficient static friction between block B and the horizontal surface is 0.25. Find the maximum weight of block A for which a system will be stationary. Oops, my bad. Alright, let me pause this for a second. Alright, final part of this, of course. You want to maybe sing a song or something back there? No. Alright, so this one here is a little bit different. Again, I'm not going to put too much narration here. I just want to get these solutions written up. There's actually a bunch of different ways to draw the force diagrams, but actually we're going to draw the force diagram about that point. Alright? Even though there's no object there, it's the intersection of the ropes. So, about that point, we have a rope going that way, we have a rope going this way, and we have a rope going this way, all kind of holding that in place. Now, this one's kind of an interesting one, right? Because let's give these names: FT1, FT2, FT3. All right, FT1. If you look at block B, FT1's pulling that way and this way. FT3 is pulling this way and this way. FT2 is pulling this way and this way. So we actually have 3 interacting objects here: the wall, the block, actually 4, right? Well, 5, 1, 2, 3, 4, and then the earth pulling on everything. So we're going to get FT1, FT2, and FT3 from what's going on with their interactions, right? We want everything to be static, so everything's going to be balanced. So that means FT1 is going to have to be equal to the force of friction on B. FT3 pulling up on A, which is pulling down at this point, has to be equal to Fg of A. FT2 is just FT2. Alright? B also has Fn, has its own Fg. Alright? So let's go ahead and figure out what FT1 and FT3 have to be equal to. Alright. And you wouldn't draw force diagrams of both A and B here. You just kind of figure out what the forces have to be and apply it to this force diagram down here. So F friction is going to be mu Fn. Alright. Which is going to be the magnitude of FT1. Keep in mind, there's no vector symbols over here. Actually, these should probably be vector symbols if I'm being more careful about things. But these are all just magnitudes. FT1, force of friction. Alright, so coefficient, it says, is 0.25. The normal force on block B is going to be 711 newtons. You don't have to multiply that by G. It already gives you weight. Alright, so that's 0.25 times 711, or about 180 newtons. 2 sig figs is plenty. All right, so it's 180 that way. So technically now, if I want to make it a vector, negative 180 newtons. All right, FT3 is going to equal MA times G. Oh, it just wants weight, right? So forget that. Just call it FGA, the weight of block A, which is what that is. So that's what we're looking for. All right, this angle here is 30 degrees. We'll put a coordinate system on here. All right, so let me go X direction, Y direction now. And I'm doing it about this point. There's not an actual object there. So the net force about that point is 0. So FT2x plus FT1 equals 0. Now you might say, why are you doing this? Well, this is what we always do. FT2y plus FT3 equals 0. Alright, so I should have broken this into components here, FT2. Alright, over here I'll just do it. FT2x equals FT2 times the cos of 30 degrees. FT2y equals FT2 times the sine of 30 degrees. Alright, so now I can plug all that stuff in here. So FT2 cos 30. FT1 we said was negative 180 newtons equals 0. In the y direction, FT2 sine of 30 degrees minus FGA equals 0. Alright, minus the weight of block A. Alright, so we have two equations, two unknowns. So we'll solve this one for FT2, the magnitude of FT2. It's 180 divided by the cos of 30. So that's 180 divided by cos of 30, which is 210 newtons. Alright, and then we just plug it in over here. So FGA equals 210 newtons times the sine of 30. FGA is 105 newtons, right? Sine of 30 is 1/2. And that's it.